All right, so what I wanted to do is review what we did in class and talk about how it all ties together with the labs and with the little mini labs that we did. So first we defined forces. So we went from kinematics into forces this week. And forces basically mean pushes and pulls. That's it. That's a really good definition of a force. Now really what matters is not what forces mean, but what they actually do to a system. So what I want to talk about first is how we're going to be labeling forces. And we're going to be using a thing called a free body diagram, which is going to be a picture of all the forces acting on something. So to do that, I want to talk about first how to label forces. So let's take a hypothetical scenario. Here's an object that I'll call A, and let's say that we're pushing it with our finger, like this. So this fingernail. So I'm actually pushing A with my finger. So here's how you label forces. To label the force on A, because I'm pushing it with my finger, okay, you use an arrow. So actually step 0 is you draw a dot for the mass. Then you use an arrow. And you label the arrow with 3 letters. And those 3 letters are the name of the force, what feels the force, and what causes the force. So here's what I mean. I will literally draw a point for the object A, and I will draw an arrow like this. I will draw an arrow, and I will label it F for force on A because my finger pushes it. That's how we label forces. Okay. So that's really the key to what we are doing and how things work with the forces. So again, this is something you're going to have to memorize. You draw a point mass. You draw a point for the mass. You name the force with a letter. What feels the force, which is A is feeling the force. This blob A is feeling the force. And what causes it, which is the finger. So again, this is one thing. This is the force on A due to F, and that's how you read it. So this is the force on A due to my finger. And that's how you read that. Okay? Now, what I want to get into today is going to get us into our mini lab. So then we had the first force that we labeled, which is this thing called gravity. So we have the weight. Actually, I'm getting ahead of myself here. Here's what I want to say. I have an object, a mass, that I'll call M. Now we know that it falls. So gravity is the force that makes things fall. And of course, we get a deeper definition when we watch The Elegant Universe. But we're going to really keep this simple. It's the force that makes things fall to the earth. So what does that mean? It always points down. So now I'm going to tell you how to label it. So again, we're going to follow this procedure here. I'm going to draw a dot for the mass, so I'll do that right here. And then I will go ahead. I will draw an arrow for the force. Now here's the thing. The letter we use for gravity is we use W. And W stands for the weight. So now you have a definition. Weight is exactly the pull of Earth's gravity on an object. So we're going to have the weight on the mass due to the Earth using this convention. Again, the name of the force is W, which is weight. What feels it in this case is M. And what makes it is E, Earth. Now, there are a few other forces here, and if you were in block 3, I kind of labeled them. I want to skip ahead to the most relevant force for the lab, which is the spring force. So the spring force comes from, for example, from the scales that we use. And the way we would label that is we'd simply say, look, so the spring forces work like this. They go away from the object always. So let me give you an example. Suppose I have some mass and I have a spring here and I'm pulling the object, okay? So I'm pulling it. This is just an example. The way I would label the spring forces, I would draw a point for the mass and I would draw an F sub S for the spring. The rule for spring forces is only one subscript. Okay, so those are the rules. So always draw spring forces going away from the object. Okay, now, so that's just a rule we follow. Now, we did a lab, and what I did was I actually had you label the letters in the lab. I had you measure these. I actually had you take these masses, and then you measured the weight. And again, so what you measured was the effect that gravity has on these objects. And of course, you got a 0.2 kilogram weight has 2 newtons of effect, 4 newtons, 6 newtons, 8 newtons, and 10 newtons. And of course, when you plot this, this actually works out really nicely. So we could actually even plot this here. We could draw arrows here and here. And just kind of get these axes labeled. I know this is not the neatest graph, but oh well. I don't have a ruler. So this would be 0.2, 0.4, 0.6, 0.8, 1.0. And again, we got 2, 4, 6, 8, 10 newtons. And of course, we get this nice, neat, linear plot. Okay. And of course, this is weight in newtons versus mass in kilograms. I want to start seeing you labeling these axes like this. It's a really important thing. And of course, when we get the slope here, the slope will actually end up being 10 newtons per kilogram. And we actually give this a name. We're going to call it, and this is interesting, we're going to call it little letter G. Very similar to a thing we measured before. And we're going to call this the gravitational field strength. So, what does the slope of this line tell you? Again, it tells us G, which is 10 newtons per kilogram, and we call that the gravitational field strength. Now, if we want to explain in our own words the difference between weight and mass, here's what we say. Weight is the effect of Earth's gravitational field strength on a mass. Mass is simply, I don't know, whatever you want to call it from chemistry. We're going to come up with a definition in physics, but for now we're going to use the chem definition, which is the amount of stuff in an object. That seems kind of like a circular definition. We're going to improve it later. So now, if we were to draw this mass and label the forces, we've learned 3 types of force here. Okay. So it would actually look like this. We draw a point mass for the object. So if we were going to label one of these masses, okay, and draw the forces, what would we have? We would have the weight on the mass going down, and we had a spring scale. And what that means is that there is a spring force from the spring scale on the object. Notice I'm following the rule here. Notice I follow the rule that says spring forces are away from the mass. How do I know this is right? If you want to, another way to check this is if you look at these two forces, they have a tug of war and cancel. So some of you, I noticed in lab, you had this drawing. You would have WME and the spring force going down like this because you were thinking of the spring being stretched. Well, if you had two forces acting like this, the thing would fall down. So you know that's wrong. The force diagrams, the free body diagrams, really do work like a real-life tug of war. So based on our previous free body diagram, what this tells us is if forces are balanced, an object remains at rest. That's our big idea. Okay. Sorry. Forces are balanced, an object remains at rest. Then we went ahead and we did this water lab. And we accelerated water to a high speed. We walked with constant speed. We turned right, we turned left, and then we abruptly stopped. So what we predicted, starting from rest, water spills. Moving at a constant rate, nothing happens. And of course, judging from people's reaction, we knew that turning right, left quickly, water spills. And of course, abruptly stop, the water spills. So, what can we say about this? Well, we actually confirmed all our predictions. So that wasn't surprising. But how do we unite all of these under one explanation? So that's really the goal. So if I had to unite these under one explanation, and we talked about this a little bit in class, the uniting explanation, and this is something we're going to practice more in class, is when the water is at rest or in motion at constant speed in a straight line, nothing happens. And there's more. If I try to speed it up, slow it down, or change its direction, it fights. It fights me. It fights the change. Okay, so there we go. So we've got a little conclusion to reach here, and I actually kind of want to write that up. So our conclusion, number one, gravity is the force that Earth exerts on objects. Sorry, weight is the gravitational force. 2, objects at rest remain at rest when forces are balanced. And 3, if you try to make an object speed up, slow down, or change direction, it will fight that change. This is called the property of inertia. Those are our 3 big ideas for the day. And we're going to take those up next time with some more lab activities. So thanks a lot.